Welcome everybody to our first lecture in Chem 20 here. This is going to be chapter 1, and I hope you guys are doing well. So the benefit of these video lectures is going to be that you could pause them, rewind them, start them over, watch them over and over again, or do it at your own pace and at your own convenient time. And so I'm hoping that with that being said, you guys are going to be okay with the with the video style lecture as opposed to trying to organize or to make it work to have a Zoom meeting, at the regularly scheduled time. So we're going to try this. Okay, so the chemical world. Now, chemistry is the science that seeks to understand what matter does and what atoms and molecules do. So virtually everything around you is composed of chemicals. Now, atoms are very small, like tiny. Now, atoms and molecules are tiny particles that compose all of what we would call common matter. Now, the atoms are bound together to form several different types of molecules. Let me show you one. And chemical bonds are the attachments that hold atoms together. So this is water. Now, water consists of 3 atoms, 1 oxygen, 2 hydrogen, bonded together, and the water molecule is what we call bent. Now, the characteristics of water molecules make water a liquid at room temperature. And so we'll come back and talk more about how we classify it as bent, and how we would know that this thing is polar, and why later we'll be able to explain, I think it's chapter 12, why it's actually a liquid when other molecules, such as, I'll give you a couple examples. Here's a lighter molecule. This is H2. This guy's H2O. And then here's a heavier molecule. So all 3 of these molecules would be, I guess here's what I'm trying to say. This heavy molecule is a gas. This light molecule is also a gas. Water, sitting somewhere in the middle, shouldn't be a different phase. Most other molecules that are in between the weights of these two are gases at room temperature. Yet water is a liquid. And so that's what makes water very special. And we'll talk about the special nature of water in later chapters. Now, there's nothing that you can hold or touch that's not made of chemicals. Chemicals make up virtually everything we come into contact with. You can see a few things here. This is presumably some sort of either coffee or flat soda. It looks like there's actually, this is a carbon dioxide molecule right here. This is a water molecule. Again, these are representations. This looks like it could be a sugar molecule. This looks like it's caffeine. And that's just from experience. I don't expect you guys to know those kind of things at the end of this class. DNA, right? The double helix from our bodies. Graphite, carbon atoms arranged in sheets that come off really easily while you write. Same atom put in a different orientation is diamonds. Now, people often have a very narrow view of chemicals, thinking of them as only dangerous poisons or pollutants, right? When we say something has chemicals in it. I once took the common name, the common name for this molecule is water, but the scientific name is dihydrogen monoxide. Already you're thinking, yeah, that sounds poisonous. I told my mom when I took chemistry a long time ago, I told her, did you know that 99.9% of all lakes, rivers, and streams have dihydrogen monoxide in them? And she was like, just as an example, right? It sounds like a chemical, but everything's a chemical. Water is a chemical. The air we breathe is a chemical. The water we drink, toothpaste, Tylenol, toilet paper, all of these things are chemicals. Now, chemistry explains the properties and behaviors of chemicals. Properties and behaviors by understanding the molecules that compose them. So that's the sort of point of doing scientific studies or chemical experiments, is to better understand properties and behaviors. Now, we get to the point where once we understand those, we can just design molecules to have the properties and behaviors that we're interested in. A good, simple definition of chemistry: the science that tries to understand how matter behaves by studying how atoms and molecules behave. All right. All right. So before we can sort of move any further with our chemistry, we need to talk about what the scientific method is. It's essentially how chemists think. So, scientific method. Now, it's a way of understanding the world. So, chemists use the scientific method, a way of learning that emphasizes the observation and experimentation. Observations, oops, too many letters, lead to experiments. To end up producing knowledge. Should have drawn a light bulb at the end result. So observations lead to experiments that will either confirm what you maybe thought. So you got to develop something called a hypothesis, which is a question. You need a question to answer. To do with an experiment, you need to have something you're trying to get at, and then whether that is a successful experiment and you prove your hypothesis right, or an experiment that says no, your hypothesis was wrong. Both of those are valuable. And so, just as a historical standpoint, the scientific method stands in contrast to the ancient Greek philosophies and the medieval applications of them that emphasized reason to produce knowledge as a result of thoughts, where you would just think about things, and if it made sense to you, it was good enough to say this is how it worked. And so that's definitely not the case with the scientific method. Observations are a result of the senses. Observations involve measuring and observing some aspect of nature. Hypotheses are tentative interpretations of those observations. Laws, which are the next sort of thing that comes out of this, summarize the results of a large number of observations. So we could say something like the law of gravity, right? You guys have heard of the law of gravity. This isn't something we made up. Gravity's a thing. Objects get pulled down at a particular rate here on Earth, and we've just documented it so much that we can say, hey, this holds true no matter where we are. It always happens. It's a law. Now, a law is different from a theory. A theory is a model that explains and gives the underlying cause for the observations and the laws. So it's not within the law of gravity to say that there's a curvature of space or that matter warps space-time. That would be in the realm of the theory of gravity. Okay, so we went over the fact that experiments are to prove your hypotheses. That being said, you have to have a hypothesis that is provable. You can't have an untestable hypothesis. Like I could say that all life came from a distant galaxy that we can't see anymore because it's so far away. But that's where all life came from. How would we ever know? One, we can't ever see it, to ever go there, to ever check, right? So that's just a terrible hypothesis on its face. Okay, let's talk about observations. Observations and how we make them. So some observations can be made with the naked eye. Other observations emerge from experiments that rely on the use of sensitive instrumentation. They usually involve measurement or description of some aspect of the physical world. And to give you an example of when this sort of became a thing that people were doing, well, first you had to have money back in the day. Scientists were people who had enough money to basically lay around and not go to work and think about and build and commission the building of sensitive equipment. So Antoine Lavoisier, circa 1940 to 1979, I think, French chemist. He got to spend a lot of his wife's money to basically build really or get built really accurate scales. So back in the early days of science, there wasn't very much in terms of instrumentation. Um, you could make scales. Weighing things was about that and keeping track of time were the two things that people were getting really good at, clockmaking and sort of making scales. It wasn't until electricity came around, that coupled with vacuum technology, sucking the air out of things, where they were able to make evacuated tubes. Of course, light bulbs come from glass blowing, and telescopes needed lenses, and so there was a lot of glass work that was going on. So you can see there was a lot of different pieces that were all just in their own areas being worked on. Now, today, we have the benefit of all those things being merged. But so Lavoisier was into mass and studying. Sorry, I used a term here that you guys don't know. Mass. Mass is how much stuff you have, and this is essentially what we equate to weight here on Earth. So Lavoisier measured the property of mass in the process of combustion. And so the observations he made had to do with burning things. Now, the mass of an object is a measure of the quantity of matter in it. And what Lavoisier did was he burned substances in a closed container. So, he put a little piece of something, and then he put a closed container on it, and he weighed it. This weighs X number of grams or whatever. And then he burned it, like I said. So then he's got some ashes. And he found out that it still weighed the same number of grams. This was the observation that he made. So there was no change in mass during the combustion. Okay, so we're going to come back to that in the next chapter. So let's just wrap this scientific method stuff up. So observations lead scientists to formulate hypotheses. His hypothesis was, I don't think, well, we'll talk about what the ramifications of his experiments were in just a second. If you come up with a good question, maybe his question was, I think the mass is going to change, right? The stuff looks like it's changed. Maybe some of the stuff disappeared into, I don't know, the ether, because that's what they used to think of. Everything in the old days was made up of, earth, wind, fire, water, and existed in the ether. So his experiment might be, or his hypothesis might be, if I put the container, here we go. If I put the lid on this while I burn it, what if nothing can escape and I can still weigh everything? Or, if everything is trapped in here and it still weighs less, then that means things just evaporate into the ether. So his experiment could have had a hypothesis along those lines. So a good hypothesis is falsifiable, meaning he can prove it wrong. Tested by experiments, you eventually modify your hypothesis based on the results of your experiments. Sometimes you discard your hypothesis altogether and replace it with an alternative. Anyways, so his hypotheses and his experiments led him to actually be able to develop a scientific law. And the scientific law in this case was the brief statement that sort of synthesizes past observations and actually will predict future ones as well. And he developed the law of the conservation of mass. I can write that here. Law of conservation of mass, which states, in a chemical reaction, mass is neither created nor destroyed. Okay, so one or more well-established hypotheses may form the basis of a scientific theory. Theories provide a broader and deeper explanation for the observations and laws. Theories are models of the way nature is. Theories often predict behavior that exists or extends well beyond the observations and laws on which they're founded. So it conveys a much deeper sort of understanding. All right, and this is a sort of flow chart of the process. Now, scientific theories are tested and validated by experiments. And another sort of discovery that came out of this new way of kind of thinking about the world, again, the scientific method, was the atomic theory of John Dalton. So let's talk about John Dalton. This is John Dalton. And theory, yeah, there's some misspells here. So this guy was able to kind of play off of the work of Lavoisier. He explained the law of conservation of mass by proposing that all matter was actually composed of small, indestructible particles called atoms. Now, Dalton's theory was a model of the physical world, and it went beyond the laws of observation of the time to explain these laws. And so a lot of people were going to be resistant to this sort of idea. Now, it helps when theories have a lot of experimental support. Now, established theories with strong experimental support are the most powerful pieces of scientific knowledge. I'll show you some pictures. So people unfamiliar with the science sometimes say, oh, that's just a theory, as if theories were mere speculations. Well-tested theories are as close to truth as we get in science. So the idea that matter is made of atoms is a theory with 200 years of experimental evidence to support it. Modern technology actually provides us with recent images such as this one. This is the characters for atom written in kanji. They are iron atoms on top of a copper surface. So this is copper and these are iron. The shape of them is actually an artifact of the processes used to see these. These are electron microscopes that make these images, and so there's a little deforming of the atom shape because of the way that this picture is taken. It's not really a picture, but the way the image is made. But we would imagine that these would be pretty symmetrical, spherical type objects, and they are. We can see that in these pictures. All right, so how do we succeed in chemistry? How do you guys succeed? So chemistry requires some curiosity on your part. Oh man, can I spell? Some curiosity and also some imagination. We can't see atoms. We can't see a lot of the molecules. We see the macro stuff. We don't see the micro or the nano stuff. And so you guys have to use your imagination sometimes. You're going to have to picture these things. Now, I did provide you with that virtual model kit on Canvas. I encourage you guys to use it every time you want to see an atom or a molecule, or spin it around, do something with it in that app. I encourage you to play with it. It's really cool. But you got to have some kind of imagination, and then you should, again, I'm talking about how to be successful. You should want to know the why of things. You should want to know why something is the way it is, and why does sugar water taste the way it does, and why does it taste different than salt water, and why can I add so much sugar to my Kool-Aid that eventually the sugar doesn't dissolve anymore? What's really happening? Right? Those are the kind of questions that I always ask myself, but that's why I got into science in the first place. I guess it depends on why you're here. So chemistry, unfortunately, also, yeah, that's fun, right? Curiosity and imagination, be successful. That's half of it. It also requires calculations. It requires math, and it requires quantification. There's quantification and there's qualification, or qualitative versus quantitative. I can say, hey, I could put my hand into two water samples, let's say, two different sinks of water, and I could say, oh, hey, one's warmer than the other. That's qualitative. That's not really sciencey. I mean, it is to a degree, but if we want to really get to the bottom of if they actually are different temperatures, or we need some numbers, and so that's when we'd say, oh, hey, this one's 40 degrees, this one's 44 degrees, and so quantification allows us to specify differences precisely. So calculation is a result
of quantification. Quantification means numbers. Calculation means, hey, what are the differences in these numbers? We're going to have to do some math. You should do your work regularly and carefully. If you do, you'll succeed. You'll be rewarded by seeing a whole new world full of molecules and atoms. You should do all the questions in the book. Well, answers to all the questions. Sorry, if they're blue questions, they should have answers to them in the back of the book. The problems, there's exercises in the problem section that are paired, and the answers to the odd-numbered exercises appear in the answer section at the back of the book. You should do the in-chapter assessments, and when you finish reading the chapter, you should read the chapter summary. All of these things will help when you are trying to work out the best study tactics or study techniques for you. So if you're curious and imaginative, if you're willing to do calculations, if you're committed to doing the material, learning the material, and if you do your homework, you should be successful in this class. Now in the next chapter, we're going to expand on this conservation of math stuff. We're going to quantify some masses, and we're going to actually do some calculations, and I'm going to introduce you to taking measurements. All right. So from what you should know from chapter 1, chemistry is a science that tries to understand what matter does by understanding what molecules do. The scientific method that chemists employ makes use of observations, hypotheses, laws, theories, and experiments, not in that order. And then analyzing and interpreting data requires a series of measurements, and we call those measurements data, and sometimes you have to graph it to see the relationships. You're going to have to graph something in the first lab that you guys do, the measurements lab. Maybe that's not true. In the density lab, lab 2, you're going to graph something. But it helps to see relationships. Okay, so I think that'll do it. All right, guys. I'll see you in the next video. See you tomorrow.